And the last thing that I want to talk about in this sort of preliminary session is proof techniques. So one of the big features of this course is going to be learning or practicing how to rigorously and carefully prove things using well-reasoned arguments. So your exposure to proofs may be varied depending on what courses you've done before, but unless you've done something like a course on algebra, it's likely you haven't come across the sort of formal reasoned proofs that we're going to be dealing with in this course in quite the same way. So a lot of the theorems that we're going to have to prove, it basically take the form of A implies B. Okay, so A is a statement of some sort. There's either statements. It might be a statement about real numbers or a statement about a particular function or something, and it's going to be a proof of the form, if A is true, then B is true. Okay, and we're going to need to prove that somehow. Now, before we just dive into the different ways of approaching this, you may not have thought of this way before, but A implies B is just a logical function which depends on the truth values of A and B. Okay, so if we were to put this in a table, then if A implies B is true, which is what we're often trying to prove, then the way we sort of think of it is that if A is true, then that implies or means that B is true, and so we say that the implication itself is a true implication. If A is true and B is false, then it's not true that A implies B, so the implication is false. Now the slightly weird thing that you might not have thought of before is if the premise or the hypothesis itself is false, then the implication value is also defined. Now you may have never thought of this ever before, so let's just write down the two additional cases. If A is false, B true, and A is false and B is false, it turns out by definition that the implication is true automatically if A is false. So you might have heard reference to some statement somewhere saying any falsehood implies any fact at all, whether true or false. And that's what we're talking about here. And it's kind of like a formal definition rather than a meaningful fact about life. But whenever we have a false statement, then by definition it implies any statement at all, whether true or false. So when we're trying to prove something, the first method that we try to use is what's called a direct proof. So a direct proof means we're going to start with the statement A. Okay, we're going to assume that A is true, which means we're here. And we're going to try to show that B is true as well. Okay, because if we can show that A being true leads to B being true, then our implication is going to automatically be true, and we're done. So this is assume A is true. Use this to show B must be true. Alright, that rules out the second row of the table, which means that the implication is going to be true. Now that's kind of what many of the proofs you will have seen in the past have been like, even if they haven't sort of stated it in this slightly weird way before. But it's just start with your hypothesis A and use it to show that B is true. If you've done that, then you've shown the implication is true, because you've ruled out the second case where the implication can be false. The second method is called proof by contradiction. So in this method, what we do is we add, instead of attacking that first row of the table, we're going to note that just get rid of my little marker there. We're going to note that the only way an implication can be false is if A is true and B is false. Okay, so we're sort of focusing our attention on this row here. The only way that this implication can be incorrect is if A is true and B is false. So we start by assuming that A is true and B is false. Okay, and if you like logic, then that can be written as A and not B. And what hopefully happens if we do that, because remember we're actually trying to prove that A implies B still. Hopefully if we assume these two things, then we'll find some contradictory fact which means it cannot be the case. Try to find a contradiction or an absurdity or some kind of fact like that that doesn't make any sense. And the final method is actually, we'll draw a new truth table, is to recast the question. So if we've got A, B, I'm also going to write down not A and not B. So we've got A can be true or false, B can be true or false, not A is just the negation of A, so it's just the opposite values each column here. Similarly, not B is going to be the opposite of B. Now what we're going to do is we're going to use our previous truth table to look at the implication not B implies not A. Okay, so remember the only way an implication can be false is if the hypothesis is true. So if not B is true, that's here or here. And the conclusion, which in this case is not A, is false, which is here. That is the only way that our implication can be false. The other three cases are going to be true automatically. And lo and behold, that truth table is exactly the same as the truth table for A implies B. So this is called proof, or proving the contrapositive. So that statement not B implies not A is called the contrapositive. And is logically equivalent to A implies B. So if we are trying to attack a proof by the contrapositive, we assume that the negation of B is true and try to derive the statement of the negation of A, whatever that may be. Now, it's all very abstract at the moment what I'm talking about. We'll do plenty of examples of these as the course goes on. But I've just wanted to sort of summarize these three techniques here in one place because we will sort of be referring to them from time to time. The other thing that we'll be getting used to is working with lots of statements about there exists and for every and all this kind of thing. And you'll expect that you'll have plenty of practice and we'll build on this over and over again as the course goes through until by the end of it you'll be seasoned professionals. Okay, but let's just do one proof just to see if we can tie some of these ideas together. Okay, so the theorem I want to prove is this one here. Theorem. So two real numbers A and B are equal if and only if, okay, that's a key word or key phrase, for every real number epsilon, or for every epsilon greater than 0, there exists, it follows, not even writing this correctly, it follows that the absolute value of A minus B is less than epsilon. Okay, so this is an equivalent characterization of equality of two numbers. Maybe a slightly strange thing to do, but what the heck, we're going to do it anyway. So first thing we want to do is we want to sort of break down the structure of this proof a wee bit. Okay, so the first thing that jumps out at us is this if and only if statement here. Okay, if and only if. That means that actually we have two things to prove. We're looking for our two statements. We've got one statement here, A and B are equal. I'll call this statement A, And then I have, for every epsilon greater than 0, it follows that absolute value of a minus b is less than epsilon. That whole big mouthful I'll call statement B. So we need to prove that A implies B and B implies C because of this if and only if statement here. Okay, so we're trying to prove that, sorry, B implies A. We're trying to prove that A and B are logically equivalent to each other. Each one implies each other. Okay, so we'll start with the first direction because it's easier. If we're going forwards, we're trying to show, so assume A is equal to B. Then we're trying to show statement B, which is that no matter what positive epsilon I choose, absolute value of A minus B is less than it, while absolute value of A minus B equals 0, which is less than epsilon for all epsilon greater than 0. So that one's easy. The other direction, we're going to attack it using contradiction. Okay, so now I'm doing B implies A. So contradiction, just recall, we take the conclusion, which in this case is A, we negate it, and we assume that the negation and the hypothesis are both true. Okay, so we're going to assume the negation of A, which is that A is not equal to B, and B itself for every epsilon A minus B is less than epsilon. This is the shorthand for every there. Okay, well, what about epsilon equals the absolute value of A minus B? Well, there's a problem here. A and B are not equal, so this is greater than 0. But A minus B is not less than epsilon because we've just set it equal to epsilon. This cannot be both equal to and less than and greater than absolute value of A minus B, so we have found a contradiction. Okay, so we're revisiting this kind of approach to proofs many, many times, but that's all for now.